Yeah, you've heard of turning points before? What's a turning point then? Yeah, but describe what it means on the graph. Wow. Well, thanks. And is it by any chance is it a point as well? Yeah, it's usually a maximum or minimum point on the graph. We had another word for this earlier in the semester when we were looking at quadratics, a vertex.
Yeah.
Or point. That's something a little bit different which we'll do as well. So we're looking at finding turning points. We know how to find a turning point for a quadratic. I'll do a super quick reminder of that. For example, you can see, if I had y equals x squared plus 4x plus 9. How did we find the turning point here? Complete the square, wasn't it? X plus 2 squared plus 5. So what's the turning point? Where is it at? -2 and 5. So this is the turning point here. But there is another way to find the turning point, and this way I'm about to show you is more useful because you can use it for any problem, not just a quadratic. What you should notice is here the slope, which we said is the derivative, is negative. Here the slope of the tangent is positive, but here at the turning point it's 0. Yeah, so whenever the derivative is 0, that means we have a turning point. And this gives us another way to find a turning point. So this is like our first result or formula. If you want to write this down, please. This is what we'll be using today. Derivative is 0.
So, it's just derivative 0, right?
Now I'll give you some examples now in a moment. I just need this is the key formula for today.
The graph has nothing to do with the turning point.
This is the turning point here.
But does it have to do with the equation you listed right now?
No. This is just an example, remind you of complete the square. Okay, you wrote this down? Yeah? Yes? Okay, let's have a look at our first example then. So we'll actually use this quadratic. Y equals x squared plus 4x plus 9, wasn't it? So the derivative here, what's that? 2x plus 4. And we need the derivative to equal 0 to find the turning point. So what does that make x equal to here?
2. No,
-2. And if I put that in here, I can get the y. And it turns out when I put the -2 in, I'll get y is 5. When I substitute the -2 in. You can check it if you wanted to on your calculator, but you do get 5. So you get the same answer as previously, -2 and 5. But like I said, the advantage here is that this works for any type of function. So now let's look at some examples where it's more complicated than a quadratic. Okay, do you have this? You have this?
Is it y equals 5?
Yeah.
Why?
Are you listening to me? Thank you. Substitute what? -2. Where? Here. Yeah. -2 squared is 4. 4 times -2 is -8. 4 minus 8 minus 5.
Oh, yeah.
-5 plus 9?
Plus
5.
Plus 5 minus 9.
5.
It was -5 plus 9.
Yeah.
Sorry, -4 plus 9, which is
Oh, yeah.
5.
Thank you.
Okay. Can I go on to another example? Yeah. Okay. Now, in this quadratic, there's only one answer. But if you remember your graphs are cubics, like this one here, there can actually be 2 turning points, like in this cubic here. So let's have a look at an example with a cubic now. And y equals 2x cubed plus 21x squared plus 72x plus 12. So, again, derivative will be 6x squared plus 42x plus 72 equals 0. I think I can divide by 6. X squared, what's this? 7, isn't it? And what's this? 12. So, 4 and a 3. So I have two turning points here, at -3 and -4. I still need to find the y's though, and I can get that, Hisham, by taking these answers for x and putting them back in here. So I'd like everybody to just type that in on the calculator, please. Put in the -3 and the -4, and then we can see what y values you get. So, you might remember when we were sketching cubics, I said at the time, we don't have any way to find the turning point, unlike a quadratic. But now we do. We can use the derivative to find the turning point.
No, -69.
For the first one?
Yeah.
And then the y? For the second one.
In the exam, they'll ask us to find.
They could ask you to find it on the graph when you draw the cubic. So what they'll do is they'll say, draw this cubic and show where the turning points are.
-68.
68 here. Okay. So I have a few more examples to do, but I want to give, I want you to be trying them as well, actually, for practice. So I think this one here, yeah, this one was question number 2. So if you could try and do number 1, and then I'll do it in a minute. Number 1 is also a cubic. No, there are no letters, they're just question numbered 1 to 28. So number 1, please. Now, there's actually many words for turning point, and I try to use as many as I can in the worksheet. So examples will be extreme points, turning points, critical points, stationary points, max-min points, and there's one that I forgot about as well, which is vertex. So actually there's many, many words that mean turning points. But in the exam, they tend to use turning point and vertex. Turning point and vertex are the two most common ones. But they use many, there's many possibilities. Okay, can you try number 1? Actually, yeah, since the two of you are just sitting there, there you go. Oh, I closed it. Oh well.
Well, let me do it. Let me do it.
Nah.
Come on, let me do it.
Yeah, I'll show.
I'll tap. First I'll tap. I'll tap.
I said I'll show.
On your phone.
I'll tap.
On your phone.
I don't have my phone.
Oh my god.
What do you mean you don't?
Yeah.
All that?
I don't believe that. Who leaves their home without a phone? Where's your phone? Okay, fine. Oh, what happened to your book?
Yes, with. Why is it with?
So you have no phone, and he has a book that's half wet.
And that's
What? Fine, fine.
You said number 1.
Number 1, please. Number 1. I'll write it on the board. I have it here. Y equals 2x cubed minus 18x squared plus 54x plus 30.
Why did we use over 4?
I think because I was thinking after a couple of more examples you can spend time working on them.
So it's pretty basic.
This one is a standard one.
Sorry, I forgot. Do you just do the first equation or the derived equation?
What do you think?
What do you?
That's what I'm asking.
No, what's your opinion? Yeah, the first one. Yeah. You know, because you're looking for the y. Alright, do we have answers?
No. Yeah.
Not yet?
No, I said no.
Yes.
You have answers over there?
Yeah. Yeah.
Yeah?
Get why. Yeah,
Nathan,
get why.
you have answers
Me a
there?
bit.
Yeah, okay, let's have a look. So the derivative will be, we're looking, 6x squared minus 36x plus 54 equals 0.
Squared minus
So x squared minus 6x plus 9 equals 0. Minus and minus, isn't it?
Yeah.
minus 3 and minus 3.
So this one has only one turning point. Yeah. So x equals 3, and we get y? 84 then. Okay, great. Now, I'm going to give you another one to try. It's a little bit more difficult. I want you to try it before I do it. I want to see what you get. So, this one is number 3 in the workbook. So, we have y equals log x power 18 minus x squared minus 16x minus 2.
Is it plus 16x?
No, minus here. Yeah.
Log.
Log, yeah. Try this one. See what you can get.
No.
Question about the log?
Yeah. Yeah. How do you do the log?
Hang on. It's x power 18. So as a little bit of a hint, remember one of the rules of logs, what can we do with powers?
18 log.
Yeah, we can bring it down. Yeah, so that's what you should do first actually.
Is the second one yes or one? Oh, it's one. Okay, no. So and then you times it with x.
One answer. How many answers did you get? 2 answers? Yeah. What were the 2 answers? One and... Yeah.
1 minus 19. Minus 9, 100.5.
Let's have a look then.
Right?
I think so. Okay guys, can we look up? Guys? Okay, 10. Thank you. So, let's have a look at this one here. The first thing I should do is take the 18 down. So, dy dx, equals 18 over x minus 2x minus 16 equals 0. Now, how can I solve this?
18x to the power of -1.
Not this, times x, yeah. 18 minus 2x squared minus 16x equals 0. So that's 2x squared plus 16. No, I'm taking it to the right. Minus 18 equals 0. I'm taking it all to the right here. So, I lost track. That's a plus, isn't it? Yeah. So now I have x squared plus 8x minus 9. Has 9 and 1. Plus 9 minus 1. So you get x equals 1 or minus 9. And do we get the y's? Yeah, what's this one?
Minus 19.
Minus 19 and
100.55.
100.
0.55. 55.
55. So I'll do 100.6. But to three significant figures, it'd actually be 101 then. Okay. So this one here has two turning points. But remember, it's a log equation. So we need to check if we can use both answers. So if I go back to the original, what is the domain for x? In other words, can I use positive, negative, 0? I can't use 0, correct. I can use positive x? Yes. What about my negative x?
No.
Can or can't?
You can power even number.
Yeah, it can work because it was x power 18. And even if this is negative, this will become positive.
Yeah, because
So,
it's even.
because it's even. So the only values of x we can't use are 0. Well, it's 0. And that's not a problem here. So this answer is fine and this answer is fine. So this one has two turning points. So I want to draw this graph to show you what it looks like. You don't need the graph for the exam, but it is good that you see the graph here to see what's happening. Y equals log, guys listen please, x power 18 minus x squared minus 16x minus 2. So let me graph that for you. Zoom out a bit. So you can see our first answer, guys, please, I'm showing you something here. Our first answer was minus, what were our two answers?
Minus 1.
1 and minus 9. So you can see here, this must be the turning point at minus 9, right here. It was minus 9 and 101. So that looks right, doesn't it? So this one is minus 9 and 101. And then this one here, what was that one?
Minus 9.
1 and minus 5? Minus 19. And if I zoom in a little bit here, here it is. It does look like it's at minus 19. But you notice that on the graph there looks like there's another turning point. Yeah, where? At 0, in the middle. It looks like there's another turning point. So it looks like there's a turning point at 0 and minus 6 or minus 70. So let's zoom in there to see what's happening. Where's center? Center and cross. Okay, so let's zoom in. So it looks like it's at minus 85. So let's zoom in at that. Now it looks like it's at minus 100. So let's zoom in again. It's going further down. So what's happening? Why when I try to zoom in is it moving down? Huh? It's a what? Yes, it is, yeah. Which means what? Yeah. as you said, the word is asymptote, but what that means is there is no value here. It's shooting down to minus infinity. So there actually isn't a turning point in the middle. When we go back to the original, let me just go back here. It looks like there's a turning point here, but actually what you can't see is the graph is shooting down to minus infinity. So there's actually only 2, not 3 turning points. But anyways, we can't use this one. Why not? Because we said x can't be 0, which is exactly what it is here. Yeah?
I have a question about how you got 100.
100. Well, they typed it in on the calculator and it looks right from the graph. So what you do is,
I know, but then can't you when you substitute minus 9 into the original equation?
correct. So the original equation, so you would need to type this in on the calculator. Log minus 9 power 18 minus 9 squared minus 16 times minus 9 minus 2.
This, the first part already gives me half an.
Yeah, but that's because you might have a bracket issue here, so you might need the brackets like this. Try it this way.
So you said something about zero, can't be 0 in the last graph?
We can't use 0 because we can't have log of 0.
Yeah, okay.
Yeah.
You're right.
Yes?
Yeah.
Yes. Okay. Continue.
Yes.
You want to write this bit down? Okay.
Why is that?
Why is what?
It gives you
Yeah, because what the calculator might... There's 2 things that you might have here. Log minus 9 power 18, and this will not work. Or log minus 9 power 18. In other words, if you don't use another set of brackets, the calculator doesn't know which of the 2 you mean. So it must be thinking you meant this originally. And this is why the error's coming about, because when it tries to do this first, it reaches an error and it can never do the power 18. But here, it does the 18 power first, which will make it positive, and then it can go into the log. So there is a big difference between the 2 of these. So I would say when using your calculator, more brackets is better. Yeah. Okay, we got this? Yeah? Okay. You can't have log of a 0. Log 0 is undefined. It's minus infinity, I think, actually. Okay.
It's an error. And log 1 is 0.
Log 1 is 0, yeah. Right, I think what I'll have you do for a few minutes, there's not... I think I'll do another example and then you can try some of these for a few minutes and we'll go on to the next topic. This lesson is not too difficult because really you're just solving equations. Yeah? So let me give you another one to try and find. Oh yes, I remember now. Somebody was asking me about was it you? About the sine graphs. So if you think about it, that's what we'll do next. When we have a sine graph here, we have turning points, don't we?
Yeah.
So we can use this method to help us find turning points. So what I'll do, I'll give you a graph. Let's say 2 sine 2x. No, actually, let's say 2 sine x plus 1, for example. We know that the maximum height will be what? If you look at this, what's the highest point here? No? 3, because of the plus 1 at the end. 3 is the highest point on this graph. Look at it, look at it.
2 plus 1, 3.
And what's the lowest point? Minus 1.
Why?
Basically because sine can go plus or minus 1. So the biggest will be 2 plus 1 and the smallest will be minus 2 plus 1. So this graph moves between, what did we just say, 3 and minus 1. So it'll go between the 2. Anyways, that's not what I want you to work out. I want to know where will the turning points happen. In other words, where should we have these points here? First find the x values. So again, derivative equals 0. Solve this. And again, we'll make the x go between 0 and 2 pi. Alright, try this for a minute. I want the turning points on this graph.
Oh, you want that?
No, what did I say about radians?
Oh.
What did I say? What did I say about radians?
Natural.
It's natural, yeah.
It's
Wholesome, it's natural, yeah. Radians is the default. So your reaction shouldn't have been, oh, you wanted it in
But I thought
radians.
you wanted, like, you know, you said it's the default, but I thought, like...
No, it's the default. So if I wrote radians, it should be like, yes, everything is right in the world. It's if I wrote degrees, you should be going, oh, he wants degrees.
Everything is right in the world.
Everything is right, good.
Yes,
Well, everything's right in the maths world then. Okay, try this one, please. Equals 0 as normal, yeah. Okay, let's have a look here. So the derivative is 2 cos x plus 0, and we want this to equal 0. So it means we want cos x to equal 0. So we have our IESS. First the inverse. So cos inverse of 0 is pi over 2. And the second answer will be 3 pi over 2? Actually, why am I doing 2 boxes? It's just a linear.
Plus the...
IESF. X equals cos inverse 0. So x equals pi over 2. And then the second answer is 2 pi minus the first answer. So that's 3 pi over 2. Yeah. Do we need extra answers? No. Do I need to simplify? No. Do I need to fix? No. So,
it's okay if you give it in, like, decimals, right? Like, you always have to give it.
they prefer this.
Yes.
Decimals is fine. So we have pi over 2 and 3 pi over 2. That's where the turning points happen. So there's actually 3 and minus 1. We actually need to get the y's now. If I put pi over 2 back in, let's see what I get. Sine pi, 1. And then the second y value will be... No, is it 1? It's 3.
3.
For the first one.
Yeah, it's crazy.
Yeah.
So this one will be 3, and the second one will be minus 1. So the first point is here, and then the second point, 3 pi over 2 minus 1 is here. This is the top and this is the bottom then. Well, it has to be. So the graph will look something like this, and it will continue between the two.
Will we get extra points if we do this? Like if they ask...
No!
No?
It's just a different way to do it. I don't think you should be doing it this way in the exam. I was just doing it to show you that you can get the same answer. Yes? Yeah. In the exam, they usually have you find the turning points of cubics. cubics is the most common one. The reason is because I think there's two answers. And the other reason is, if they ask you for the turning point with a quadratic, you could always use completing the square. But with cubics, you must use the derivative. You understand? You
Yeah.
can't use complete the square for a cubic.
So how often is the first principle expression?
Not often, but it has been common recently. So there's a low chance of it coming up, but not zero chance. Okay, so what I want you to do for a few minutes before we look at the next topic is to try some questions from this worksheet. Basically, the last few questions would be enough. 22 to 28, so that's like the last 6 on the page. Yeah.
How did you get the cosine x equals 0?
How did I get what?
Cos x equals 0.
Yeah, the rule is you make the derivative equal 0, and this is the derivative. So I make it equal to 0. Oh, how did I go from here to here? I divide by...
This one, you went from the one above.
Oh, here to here. Derivative of sine, cos. Derivative of 1, 0. Equals 0. Why equals 0? Because to find the turning point, I need this to be 0. I need a 0 here. Are you sure it's okay?
Yeah.
Are you sure? Okay.
Sir?
Right, can you try these for a few minutes?
22 and above, right?
No, 22 and below, 22 to 28. Oh wait, well actually, okay, it depends if you're looking at the page or looking at the number line.
So like that, yes, number line.
If you're looking at the page, it's 22 and below. If you're thinking about it as a number line, it's 22 and above.
Yeah.
It's semantics. Just do 22 onwards. 22 onwards.
And below 26.
Can I close this? Hisham?
Yes.
I can close this? Yes?